In this video, I'm going to discuss two-way ANOVA and interactions. I don't love how your book addressed the two-way ANOVA and interactions, but on a conceptual level, this is one of the more interesting concepts that you might see more often in your own life and work. To help explain the two-way ANOVA and how it helps us identify interactions, I'll give you an example from my own life. Two years ago, I ran a Ragnar Trail relay with 7 of my friends. That's me in the bottom right. If you're not familiar with a Ragnar Trail relay, it is when 8 team members take turns running 3, 5, and 8-mile races over mountainous terrain. As soon as all the team members have completed the legs, the race is over. So you may have already figured out that some of the running happened throughout the night. So I might have some research questions if I'm trying to estimate how long the race would take us beforehand. Before the race, we made an overall estimate of how long the race would take us based on our average running paces. And here was our plan. My schedule is highlighted in yellow. And based on this schedule, we anticipated the race to take 23 hours and 50 minutes. But was our prediction even close? Let's start with one research question. Is there a significant difference between a person's pace for the 3-mile leg as opposed to the 5-mile leg? You would think that running the 5-mile leg would be slower, the pace per mile, but is it significantly slower? A second research question might be, is there a significant difference in pace between running at night versus running during the day? Again, it would make sense that running at night is slower, but is that actually the case? I could do 2 separate t-tests, measuring pace in the 3-mile run versus the 5-mile run, and pace at night versus during the day. But I couldn't look at the 2 variables, time of day and length of leg, in combination. Why would I want to do this? Well, I'll explain. To do this, I'm making up some Ragnar data from here on to illustrate a point. Let's say I set up a two-way ANOVA looking at the effect of the independent variables of A, length of race leg, and B, time of day, on pace per mile. I might gather the times of all the previous runners who have run the same trail course and enter them into the two-way ANOVA formula. First, the results will let me know if there's a main effect for length of leg on running pace. In other words, the ANOVA procedure essentially conducts a t-test to see if the 3-mile run or the 5-mile run are significantly different in the running pace that they produce. And using this made-up data, we see that it does. We'll pretend for a moment that the data showed significant mean differences in addition to what we're seeing on the graph. We see that there's a difference. We don't really know if it's significant without doing the test, but anyway. The pace per mile is actually slower with the shorter leg, and that's something I definitely didn't anticipate. So when I'm running a 3-mile leg, my average pace is going to be 8.91 minutes per mile. When I run a 5-mile leg, it's going to be 8.49 minutes per mile. So that did surprise me, but the pace of the 3-mile, according to these data, is significantly slower. So we're going to take a look also at the main effect of the time of day on the pace, night or day. Once again, the ANOVA procedure is essentially conducting a t-test to see if there's a significant difference in mean running pace at day or night. And voila, there is a difference between day and night running, as you can see in this graph. The pace at night is definitely slower at 9.05 minutes per mile. So night running is slower as predicted. So as I'm planning how long our Ragnar might take, I can make adjustments to account for the fact that all 3-mile legs are going to be slower, and any legs that happen to take place at night will be slower, right? Well, not so fast. ANOVA also looks at the 2 factors of time of day and length of leg in combination to see if there is what is called an interaction effect. Here is a graph that shows how these 2 factors operate when they are combined. And we see a couple of interesting things when we look at the 2 factors in combination. First of all, let's look at the 5-mile run, which is in orange. And you can see between day and night, there's hardly a difference between the pace between day and night for the 5-mile run. So not much of a difference there. We also see that for the 3-mile run during the day and the 5-mile run during the day, there's very, very small difference there too. So we had seen these main effects, but when we look at this graph, we're really not seeing relationships until we get to this area right over here. This is where all the action is actually happening. The pace per mile for the 3-mile run at night is 9.58 minutes per mile, and the pace is 8.52 minutes per mile for the 5-mile run at night. So something's happening here that's unexpected. The 3-mile run at night is diverging a little bit and is taking just a lot more time for some reason. And as it turns out in our mythical example, let's just say that 3-mile run is rockier and less well lit at night, and therefore runners have to go very slowly to try to avoid tripping over rocks. And then that way, that would be an explanation for why running the 3-mile race would be so much slower than the 5-mile race at night. So this is called an interaction, and something that tips us off that it's an interaction is that the lines are crossing or they're diverging in a certain way. And so I'm going to show you as a counterpoint what it would look like if we didn't have an interaction between these two variables. And this is what it would look like if we didn't have an interaction. So for example, for the 3-mile run, day will be easier than night. For the 5-mile run, day is easier than night. There's no change. There's no interaction between the two. They're not crossing. They're not interacting in any way, shape, or form. And also, in the daytime, my 3 miles is going to be quicker than my 5 miles. And at night, my 3 mile is going to be quicker than my 5 miles. And so this is an example of main effects with no interaction. And so when we see, for example, lines crossing in a graph, then we know that there's some sort of an interaction happening, that something in one variable is causing change in another variable. So I'm going to give you a helpful way to think about interaction effects. Are you ready? Just think of the words, it depends. And here's what I mean. For my Ragnar research question, does pace change according to the time of day? I would answer, it depends, as it depends on whether I'm running the 3-mile leg or the 5-mile leg at night. So it depends is going to be a word that some words that we're going to use when we're talking about interactions. And by the way, it took us 25 hours and 54 minutes to complete our Ragnar. And what we didn't plan for was hot temperatures in November and a lot of sand on the 8-mile leg. But to sum up, I'm going to show you 3 slides that might also help you to understand main and interaction effects. Feel free to pause the video to take them in. And as you look at these slides, it might help to have some actual variables to work with. So take a minute to write down what's on this slide. Go ahead and pause your video and I will wait for you. So what we're going to be talking about in the next couple of slides is looking at age and gender as independent variables that might influence the number of trips to Target somebody makes in a month. And so for age, we have 1 category for young, and the 2 category indicates older. And for gender, 1 is males and 2 is females. And so that gives us 4 different categories of people we're looking at. Young males, young females, old females. And again, the dependent variable is how many trips to the store Target they make in a month. Let's take a look at some possible results for this study. And what we're going to do with this first slide is we're going to look at something called the marginal means. And these are the means that are on the edges of our table. And so these give us the means for the different main effects. And so for example, if we look at the age variable here, and 1 is young, the mean for young people who go to Target is 1 visit per month. And for older people, the mean for going to Target is 5 times per month. And now we're going to go to gender. In this table, 1 represents males, so the mean Target visits for males is 5, and the mean Target visits for females is 1. So it looks like males are strolling the Target aisles more often than females, and it looks like older people are strolling the Target aisles more often than younger people. So again, More males are going to target, but is that true for all males, or does it depend on age? For that it depends question, we have to go to the means inside the table. So we're going to look at these numbers on the inside. As we look at these four means, which one number stands out? Yes, there's actually one group that's significantly different from the rest. And that is a group of older males. Older males go to target 9 times a month, and everybody else goes to target 1 times a month. So the question of do males or females visit target more often, the best answer would be it depends, because it really depends on the age of the males. It wouldn't really be appropriate to say that all males visit target more frequently, because it really is just the older males that are visiting target more frequently. So whether or not males visit target depends on this other variable of age. And here's an example of when there's a main effect for age for variable A right here, with older having a score of 7 and the younger people having a score of 3. But there doesn't seem to be a main effect for gender over here, with both males and females scoring a 5. But if we look at the means in the middle, something odd is going on again. The real difference that over here is represented over here with the males. Young males have a score of 1, and older males have a score of 9. So the difference in target visits between young and old is actually only seen in males. It's really not a female thing. Even though the overall mean took into account all males and all females, it depends on the age once again. So this is an example of when there's a main effect for age, there's not a main effect for gender, but there is still an interaction. In this last slide, we would be totally led astray if we only looked at the main effects. So let's look at the means, the marginal means. They're all 5. They're all exactly the same. And so if I only looked at the marginal means, if I only looked at the main effects, I would say there's no difference between old and young and men and women in terms of who's going to target. But if you look a little further for an interaction, you will see that there are real differences in males and females depending on age. Once again, it depends. Or you could say between old and young, depending on gender. In this slide, we see that older males and younger females are the frequent target shoppers. So in this case, there was not a main effect for A, there was not a main effect for B, but there was an interaction between A and B. So take some time to let interaction effects percolate. It's yet another way that you can avoid being bamboozled by statistics. If someone claims some mean difference between two groups, for example, you can ask, perhaps to yourself, does that difference vary according to some other factor? Is something else at play? What might make me respond, it depends, to what they are claiming? And one final note, we are 2/3 of the way to the finish line in this course. Hang in there and dig deep and celebrate how far you've come thus far.